Okay, so today we will be starting to discuss the other two examples. If you remember, on Tuesday we had studied the Dirac delta potential. We found the bound states, and what we had done was, if we have this solution, the scattering solution, e to power I k dot z k dot r plus f, which will depend on our energy and also on the directions, e to power I kr over r. This is in 3 dimensions. In 1-dimensional example that we discussed, the Dirac delta, there is no 1 over r. And we had seen that if we take k to I times kappa, then f of I kappa has a pole at the location of the bound state. So this basically allows us to relate the bound state problem to the scattering problem. So if somehow we can calculate the scattering amplitude, this f, in an analytical form, by just using analytical continuation, we can just obtain also the bound states of the problem. Now today we will see we will start with the example of a potential well. This will be the first example where we will take the potential to be some V0 times Dirac delta R, not the vector, the magnitude, not even the Dirac delta, some unit step. Theta A minus R, where V0 you will assume to be a negative number. So this is our potential well. So basically it looks like this one. As a function of the radius, this is our potential. Now this problem is we can solve it exactly, and we can calculate the scattering amplitude exactly, the bound state exactly. So let's first start with the bound states. Now, by bound states, what I mean by states that are localized in a region of space. They don't extend until infinity. They are not propagating states. They're just localized solutions. And in this problem, we will see that if the well is very shallow, then there won't be any bound states. As we increase the depth of the potential well, we will start to have 1, 2, etc. bound states. And just for simplicity, I will only deal with the case L is equal to 0. Now, the generalization to arbitrary L is also kind of trivial in the conceptual sense, but technically it just complicates the calculation. So I will restrict myself to the L equal to 0. Now, again, as in every spherical symmetric 3-dimensional problem, I will define my eigenstates to be the radial some function of the radius divided by r multiplied by the spherical harmonics, where in my case L and M will be 0, U of r over r, then 1 over square root of 4 pi. And the U will satisfy this equation over 2m d squared U by dr squared plus V of r U, this is equal to E times U. This is the eigenvalue equation that we need to solve. Let me put in the potential. Plus V0 theta A minus R U, this is equal to EU. Now I will first make some change of variables so that I will have dimensionless parameters in my problem. So let us first define the radius in terms of A, the multiples of A. So this will convert my equation to minus h bar squared over 2m d squared U by A squared dx squared plus V0 theta A 1 minus x U, this is equal to EU, or minus d squared U by dx squared plus 2m v0 a over h bar squared theta 1 minus x. Well, the a doesn't change anything in the unit step. It's a positive number. Times u, this is equal to 2me over h bar squared u. Now I will just call this coefficient, all of it, lambda. And remember, lambda is a negative number. And this, I will just call it epsilon. Or let's say I will call this one small v0. So this is my equation. d squared u by dx squared plus v0 theta 1 minus x u, this is equal to epsilon u. How do you proceed to solve this equation? I will separate the regions. For x less than 1 and x large, for x less than 1, the equation is just minus d squared u by dx squared plus v0 theta 1 minus, no, theta is not there, u, this is equal to epsilon u, or minus d squared u by dx squared, or plus, this is equal to minus epsilon minus v0 of u. Now we are looking for the energies that are larger than v0 but smaller than epsilon. That is what we will be calling the bound state, because if the energy is positive, it can go up to infinity. If the energy is less than v0, well, it cannot be. So epsilon, we are looking for solutions for epsilon which is less than 0 but larger than v0. So epsilon minus v0, this is a positive number, and that positive number I will just call k squared. Now I can just trivially solve this equation. U is a times sine kx. Now I have also used the boundary condition. U at x is equal to 0 should be equal to 0. Otherwise the wave function at 0 will diverge. Remember, my wave function, my full wave function is u over r. That should be finite. Then we can go to the other limit, x is larger than 1. Now if x is larger than 1, the equation is d squared u by dx squared. This is equal to minus epsilon u. This time minus epsilon is a positive number. So this whole thing I define as kappa squared. This is equal to minus epsilon, or the absolute value of epsilon. And the solutions are decaying solutions. We are looking for the solution that goes to 0 at infinity. The other one will not be normalizable. So we have this u is equal to b times e to power minus kappa times x. This is the solution I have. So if you just combine these two, u is equal to a times sine kx if x is less than 1, and b times e to power minus kappa x if x is larger than 1. Now I have the boundary conditions that x is equal to 1. Now at x is equal to, let me just rewrite this solution as this way. And I'm just redefining b. Now the boundary condition that x is equal to 1 is that the wave function has to be continuous. And this tells me that a times sine k is equal to b. The left-hand side is if I approach x is equal to 1 from the origin. The right-hand side, if I approach x is equal to 1 from the infinity. These two limits should be equal. And so my wave function just becomes, let's just factor out a sine ka sine kx if x is less than 1, and sine k e to power minus kappa x minus 1 if x is larger than 1. And the eigenvalue we can determine by the continuity of the derivative. Since the potential is finite, and if the potential contained the Dirac deltas, the derivative wouldn't be continuous. but since the potential doesn't contain any Dirac delta, it's a finite number everywhere. If you just integrate this Schrödinger equation from the left of x is equal to 1 to the right of x is equal to 1, you can just actually show that the u should be continuous. The derivative of u is continuous. And if you just take the derivatives of our potential, our solution for x is less than 1, you get k times cosine k at x is equal to 1. This is the derivative on the left of x equal to 1. On the right of x is equal to 1, the derivative is minus k times kappa times sine k. So the solutions of this equation tell me the bound states. If I have a solution, I have a bound state. If I don't have any solution, then there is no bound state. And also keep in mind that what we have, the definitions of k and kappa, k squared is epsilon minus v0, and kappa squared is equal to minus epsilon. So you can just take the absolute values, they can take the square roots and put it in the equation, and for a given v0 you can determine the possible values of epsilon. So let's see whether we have solutions or not. So this is, well, I had already prepared it. So this is epsilon plus the absolute value of v0, or epsilon minus v0 square root. This is nothing but k, the square root. Square root of minus epsilon is nothing but my kappa. So the left-hand side of this equation is k over kappa. And if you look at our condition, k over kappa should be equal to minus tangent of k. So k over kappa, this is the first function. This function is k over kappa. And this is the minus tangent of k. So both of these functions should be equal if we are to have a solution. Now, to find the solutions, you can just plot both of them, and if the curves are intersect, then at the intersection point you have a solution. So I'm just plotting both the left-hand side and the right-hand side as a function of the energy epsilon. Let's start with the absolute value of v0 from some small value. If v0 is small, in this case v0 is minus 1, absolute value is 1, you see that the right-hand side is the blue one, the left-hand side is the orange one. So there is no intersection. These two curves do not intersect, there is no solution, there is no bound state. So the potential well is too shallow to have a bound state, it cannot bind. If we increase the depth of the potential, still no bound state. Now for this value, well, before this value, a bound state appears somewhere over here, when the epsilon is something like minus 0.4 in suitable units. So this is one bound state. If you increase it further, the depth, still only one, only one, only one, only one. Now there appears a second one. Well, it's not shown in this figure, but somewhere over here. Very slightly bound state, a very small energy. Well, if you increase the potential well, the depth of the well, it has a larger binding energy. So now we have two bound states. And if you just increase the depth, you will get the third bound state, the fifth bound state. But one nice thing, interesting thing is that you have a finite number of bound states in this problem. And it depends on the depth. Now let's look at the scattering problem within the same potential. Now this is our equation. Now this time we are studying solutions with epsilon larger than 0. Well, our strategy will be exactly the same. We will solve for x is less than 0. We will solve for x is larger than 1, sorry. For x is less than 1, the equation is minus d squared u by dx squared plus v0 equal to epsilon u, or minus d squared u by dx squared. This is equal to epsilon minus v0 times u. And this is a positive number. Let's just call it k1 squared this time. This is the wave vector in the potential well. And the solution AU is equal to A sine k1 of x. Now we can look for a solution when x is larger than 1. Well, when x is larger than 1, there is no potential term. So minus d squared u by dx squared, this is equal to epsilon u. Epsilon is a positive number. I will just call it k squared. So I have two solutions. Now in the previous case we had only one solution that was normalizable. The bound states wave functions have to be normalizable, and it was a decaying solution. Now in this case it's an oscillating solution. And there are two oscillating solutions, so we can write the general solution as b times e to power I kx x minus 1 plus c times e to power minus I k x minus 1. Now b, if you just remember the three-dimensional problem, b is just a spherically outgoing wave, c is a spherically ingoing wave. Now let's find b and c. We have the continuity of the wave function, and from the continuity of the wave function, if you just take this expression inside the shell, inside the potential well, this is for outside the potential well, and so the continuity just gives me a sine k1 is equal to b plus c, and the continuity of the derivative tells me k1 times a cosine k1. This is equal to ik times b minus c. And then we can solve for b and c. b is equal to 1 over 2 a sine k1 plus k1 over ik a cosine k1, and c is equal to 1 over 2 a sine k1 minus k1 over ik a cosine k1. And these are the solutions for b and c. Now if you look at the b and c values, c is nothing but the conjugate. So if you look at the initial solution, the solution here we have this is equal to c times e to power ik in parentheses e to power minus ikx plus b times e to power minus 2ik divided by c times e to power I kx. This is our u. So our wave function is just c times e to power I k. This is just a normalization. E to power minus I k a, no, k over a times r plus b times e to the power minus 2I k over c e to the power I kr over a. I just replaced x by r over a. Now this is an ingoing spherical wave, and this is an outgoing spherical wave. And if you remember our discussion, the general discussion, we said that, okay, if we are looking for a spherical, for a scattering solution with an incoming plane wave, then psi was e to the power I kr plus f e to the power I kr over r. And then if you remember our discussion about the cross-section, we said, okay, e to the power I kr, we can also write it in terms of spherical harmonics. And then when we write it in terms of spherical harmonics, one thing that we had observed was if we write the plane wave also as an ingoing wave plus an outgoing wave, that we can express the e to the power I kr in such a form. In the eigenstate, if we have a spherical symmetric wave potential, the outgoing wave is nothing but the outgoing wave, there's no possibility. The only option is it should be e to the power I k over a r over r. That is the only outgoing wave solution we can have. The only thing we have, the ingoing wave can acquire a phase. And that phase we had defined as, if you remember, e to the power 2I delta L. Well, this is our phase. This is the phase shift. In terms of this phase shift, the cross-section F was just, I think there was a square root of 4 pi, square root of 2L plus 1, e to the power I delta L sine delta L. So this was the differential cross-section, the scattering amplitude we had. And PL cosine theta. And the cross-section was the sum over 4 pi times 2L plus 1 sine squared delta L. Now, let's just define it by FL. Well, in this case, we are looking at L is equal to 0. For every L, you will see that the solution for every L will be just this term with some coefficient, plus this term with a coefficient that has a unit norm. So this term, this b e to the power minus 2I k over c has unit norm because we know that b and c are just complex conjugates of each other. Now we can define the, let's say, this one only, this one, sigma L. Let me call the square root of, or let me just call it FL. Let's look at this FL. This is e to the power no, sorry, this is not FL, this is my FL. FL is e to the power I delta L times sine delta L. This is e to the power 2I delta L minus 1 over 2I. So we already know what e to the power 2I delta L is. So it's just this one. This is equal to b times e to the power minus 2ik minus 1 over, now here I have a c over 2. Or we can also write this as b times e to the power minus 2ik minus c over 2c. Now, if you remember our discussion about the one-dimensional Dirac delta, to find the bound state, what we had done was just take k. So let's see what and take k to I kappa. And remember, k squared is epsilon. So just replacing K with I kappa, we are basically going from positive energy to the negative energies. That's what we are doing. We are taking epsilon to be negative instead of positive. And the bound states should be when this term over here, this is diverges for kappa. If we can find the kappa for which that term diverges, then we are done. That is where we have the bound states. Now let's pick up this C. Now you see this term diverges if C is 0. That is where we have the bound states. This is our C. C is a function of K. Let's just look at C times I kappa. Well, this is 1 over 2A sine K1. Well, I kappa, instead of K, if we put I kappa, this becomes plus K1 over kappa times cosine K1. This should be 0 if we have a bound state. Or K1 over kappa should be equal to minus tangent K1. Remember, K1 is the wave vector in the potential. Well, this is nothing but our previous bound state condition. This was our previous condition. This is the new condition for the divergence of the scattering amplitude. They are identical. So again, what we do is we calculate the scattering amplitude. We analytically continue the scattering amplitude, in this case, to negative values of the energy. And if there is a pole in the scattering amplitude for negative values of the energy, it corresponds to our bound states. Of course, in this case, it doesn't seem to be, we can just solve it, just look for bound states directly in a straightforward manner, so why bother about the scattering amplitudes? But for example, if you would like to go to a field theoretical framework where you don't have potentials, there are all the exchanges, you can still calculate the scattering amplitude. If you calculate the scattering amplitude, it's a relativistic framework, and the potentials are not relativistic. I mean, it's just action at a distance whenever you write a potential. So in a relativistic framework, you don't have potentials that act at a distance. So you cannot write down a Schrödinger equation and solve it. But still, you can look for scattering solutions, and if you can analytically continue it to negative energy solutions, and if you find a pole there, then you have a bound state. Now, the other example will be a bit more interesting. Let's have a shell potential. No. We did the one-dimensional Dirac delta, but this is three-dimensional shell. So basically, just imagine, does anyone of you have a water bottle?
Okay, I can imagine.
Yeah,
So I remember writing, but you
No. I mean, on Monday, what I said was we will be studying 3 examples. So we already discussed the one-dimensional Dirac delta. That was the first example. The second example was this potential well. And the third one is this shell potential. It's basically you have a spherical object, spherical shell, and well, basically you have an empty spherical shell. If you put a particle inside, depending on the strength of this potential, it will stay there or it might tunnel out of this shell. And if you just send particles from the outside, then it can also just bounce back or tunnel through. And you can also think of it as the limit of this potential. Such a potential barrier. So let's say the thickness is delta, and the height is lambda over delta. So for a finite delta, for a finite lambda, we don't really have any eigenstates inside this shell. So if you put a particle inside this shell, it can tunnel out. So that's not an eigenstate. So it will be changing in time. But if lambda goes to infinity, you have a potential barrier that is infinitely high. So the tunneling probability is 0. So particles cannot tunnel through. So whatever you put inside stays inside. So we have bound eigenstates in our shell, and there are also other eigenstates outside the shell. Outside the shell, the eigenstates, they form a continuum. They can have all possible energies. Inside the shell, we will have discrete energy levels. So let's first study that problem. Energy eigenvalues of bound states. As lambda goes to infinity. Because in this limit, we know that there are bound states. Now, we will basically repeat more or less the same thing. We are looking for solutions that for r less than a, they will satisfy, the u will satisfy minus h bar squared. Well, let me just copy it. It's basically the same equation. Let us also copy the definitions of these parameters. Okay, so by the way, this is a squared. Here I also have an a squared. This is lambda this time. Let me call this lambda tilde. This is my lambda tilde. I don't have a square in A. Because from the Dirac delta, I get a 1 over A. In the unit step, I didn't get this 1 over A, but from the definition of the Dirac delta, when we take A out of the Dirac delta, it just comes 1 over A. And epsilon is 2m e A squared over h bar squared. So this is the equation that we need to solve and find the energy eigenvalues. And we already know that we are looking for the bound state solutions which are trapped inside our shell, and this lambda tilde is infinite in this case. And inside the shell, our equation is minus d squared u by dx squared. This is equal to epsilon u, and epsilon is positive. So we can just call it k squared. So the solutions are u of x is equal to some a sine kx. U has to be 0 at x is equal to 0, and it also has to be 0 when x is equal to 1. X is equal to 1 is where I have this shell, this Dirac delta. There it should also be 0, so k should take values n pi. Let's just call kn. N is equal to 1, 2, etc. So we have all these infinitely many solutions, discrete solutions. The energy eigenvalues epsilon n is equal to kn squared, n squared, pi squared. And if you can just use the definition of epsilon to find the energy eigenvalues. So this is kind of not that interesting this much. But the next step will be kind of interesting. Now we will be taking lambda to be finite. These are the eigenstates if lambda is infinite. And if you create a particle in this state, in one of these states, it will just stay there. It will not change, it will not leak out, etc. Now, when lambda is finite, what happens is there is a finite probability that even if you put a particle in one of these states, there is a finite probability that it will tunnel out. But if lambda is very large, it will take a very long time for the particle to tunnel out. So it will stay inside for a very long time. Well, depending on the value of the lambda, that you can arrange that time to be the age of the universe. So practically there is no way you can tell whether it is a bound state, it's an eigenstate or not. And so what we expect is if we put a particle there, it will be a long-lived particle, but eventually it will decay. So that is what we call a resonance. A resonance is a long-lived state. No, it's a long-lived state. So if lambda is large enough, you can identify these states that if you create a particle in that state, it will stay in that state for a very long time. So although it's not an eigenstate, it's very close to being an eigenstate. So these will be the resonances. Let's give a short break now. Rather than continuing with the solution. So in the next hour, we can just solve it, study it without giving a break. But that's kind of what we are expecting. Now what we will be doing is just look for the pole in the scattering amplitude. We will solve the scattering amplitude, look for poles, but this time the poles will again be in the imaginary wave vector, but it won't be pure imaginary. It will have a real part and an imaginary part. So in the previous case, pure imaginary k just means negative energies. In this one, we don't have negative energies. K vector is not pure imaginary, so energy is not pure real. So it has a real part and it has a imaginary part, the energy itself. And then we will see what they are, what the real part corresponds to. Now, any questions before the break? Okay, so let's give a short break, 5 minutes, and then we will continue.